Good afternoon, bon après-midi. Welcome to this edition of the Physical Society Colloquium, the final edition for the academic year 2020-2021. I'm coming to you live from the brutalist majesty of the Rutherford Physics Building at McGill University in beautiful downtown Montreal, with concrete walls as thick and dense as a text by Misner, Thorne, and Wheeler. If you are in the Zoom session and you prefer not to be recorded or live streamed, please log out of Zoom and join us via YouTube. This afternoon, we will have a 45-minute talk, followed by 15 minutes of questions and answers. To ask a question in Zoom following the talk, please use the raise hand feature. To ask a question in YouTube, please enter it into the chat. The questions will be relayed to me by my sidekick following the talk. If you prefer to ask clarifying questions during the talk, please enter them into the chat, and I will try to raise them with the speaker if possible. After the Q&A session at the end of the talk, the live stream and recording will stop. Professors will be asked to log out of the Zoom session, and undergrads, grads, and postdocs, as well as other non-faculty in the Zoom session, will be invited to the après colloque, a chance to get to know the speaker in a more intimate setting. With that, I will now pass to Professor Charles Gale to introduce the speaker. Charles.
Thank you, Bill. So today we're very happy to greet Professor Luciano Rezzolla from the Goethe University in Frankfurt. Luciano got his PhD from SISA, the International School for Advanced Studies in Trieste, Italy. After graduating, he went to the University of Illinois at Urbana for some time as a postdoc. He returned to SISA. Then he was appointed head of numerical relativity group at the Albert Einstein Institute of the Max Planck Institute for Gravitational Physics in Potsdam, Germany. Stayed there for 8 years. And he went to the position he now occupies now. Since 2013, he is the chair of theoretical astrophysics at the Institute for Theoretical Physics of the Goethe University in Frankfurt. Luciano is renowned for his theoretical astrophysics work. For his work in multi-messenger astronomy, he co-authored an important and popular textbook, Relativistic Hadronics, published by Oxford University Press. If you go to YouTube after the talk, if you go to YouTube and search for Luciano's name, you'll see many of his simulations and many of his calculations. I recommend it. It's actually very, very good. Luciano has won many awards and prizes, far too many to be mentioned here, but let me just mention a few. So in 2017, he was awarded the Karl Schwarzschild Prize from the Walter Greiner Foundation in Frankfurt. He shared the 2020 Breakthrough Prize in Fundamental Physics as part of the Event Horizon Telescope collaboration. And the year before that, he was appointed the Andrews Professor of Astronomy, which is the named chair at Trinity College in Dublin, Ireland, which is incidentally the same chair once occupied by Sir William Rowan Hamilton. Yes, that Hamilton. In the last couple of years, we've seen a remarkable convergence of high-energy nuclear physics, particle physics, and astrophysics. And this is what we're going to hear about today, partly. So I'm happy to pass it on to Luciano, who's going to tell us about Einstein's richest laboratory. Luciano, take it away.
Okay, well, thank you very much. Welcome everybody to this seminar. I'm still unclear how is it that it is the last colloquium of your academic year. Here the academic year is just halfway through, but I'm glad for you. So I would like to thank Charles for the kind invitation and for allowing me to present this. And I was asking what topic I should cover. I could, present other results on the supermassive black hole M87 star or on neutron stars. This is two other topics I've spent quite some time over the last couple of years. There was a clear selection from binary neutron stars. This is what I will present today. So this is a little and short plan of my talk. I will first try to convince you that binary neutron star mergers are fantastic laboratories. In fact, possibly the richest laboratory to study physics. I will explain how you can understand the equation of state by doing gravitational wave spectroscopy, maybe a funny concept for you. And I will tell you how, neutron stars, when they emerge, they don't emit gravitational waves, but they also shine in light. And I will tell you what we've learned. Very briefly, I will tell you what we learned from GW170817, this event that happened in 2017, and that was the first merger of neutron star binary. And as a concluding part of my talk, I will going on to more speculative path, which is the one that wants to look at signature of quark hadron phase transition from these events. So let me start by saying that as a theorist, we are trained to take a complex problem and to dissect it into its most elementary parts. So at the end of the day, when you think about it, binary neutron star mergers are nothing else but a two-body problem. So a problem where you have two objects which are interacting. In this case, interaction is gravitational. You assign some momenta, linear momenta, to these objects, and you hope that these momenta are such that they will be bound, and in particular on quasi-circular orbits. And of course, you can think that this is true for two neutron stars, but also for two black holes. In the case of two black holes, you can think this is just a scattering problem. You have two objects here you can start with, two black holes, and you, as a result of this scattering, you produce a black hole plus gravitational waves. And this is something that we were able to compute theoretically already in 2006, but then we've seen it in 2015 with this famous event, the first gravitational wave event. Now, when you think about it, neutron stars are very similar in this respect, okay? You can still think this is a scattering problem. You start with two neutron stars, and actually, eventually you end up again with a black hole plus gravitational wave. So, it's a very similar process, but there are some important and subtle differences. The first one is that when two neutron stars merge, you don't produce a black hole right away, or in general, you do not. You produce an object which is called a hypermassive neutron star. This is an object which cannot exist in nature. You cannot build this through quasi-stationary equilibrium changes, but you can produce it in a metastable equilibrium. That's exactly what nature does. And because it is unstable, will eventually collapse into a black hole, a rotating black hole, plus a certain amount of matter around it. We call this a torus. And when the torus is fully accreted onto a black hole, well, that's when you end up with a black hole plus gravitational waves. And luckily for us, we've seen this happen in reality. And this has happened in this event, GW 170817, where you see that a gravitational wave signal is then emerging a few seconds later, 1.74 seconds later, in terms of light. Now, these phases that I was mentioning, well, they are the most difficult parts to study, but they are also where all the interesting things happen. In particular, if we understand this part well, and I'll try to explain, we have a handle to understand what is the interior of neutron star. We call this the equation of state. If we understand what happens in this part of the picture, that is what happens when you have a black hole and a torus, then chances are we can understand what produces short gamma ray bursts, where we see a jet being emanating from these objects, an ultra-relativistic jet. And another important aspect, which is maybe not so surprising, is that part of the matter that is composing the two stars is ejected. This is not surprising to think that you're smashing two compact objects which have a large mass at a fraction of speed of light. Well, the system has enough energy that some of its mass, a very tiny amount, of the order of 1%, will be unbound. And this little matter that is unbound is extremely important, because we believe that some of the elements, in particular the elements we cherish most, like gold and platinum, they are produced by binary neutron star mergers. It's not yet clear whether neutron stars actually can do coins and build coins, but they certainly can produce gold. So let me tell you how you can possibly study such a complicated problem. It's complicated because you are bringing into this picture not only strong gravity through the Einstein's equation, but also relativistic aerodynamics or magneto-aerodynamics, which we express in terms of these conservation laws for the energy momentum and the best mass current. Then you have a complicated equation of state where you try to relate pressure to density, internal energy, composition, and whatnot. And because you have possibly electromagnetic fields, we'll have additional conservation equations, essentially the Maxwell equations. And that means that your energy momentum tensor that appears here on your right-hand side of the Einstein's equation is really the combination of a number of elements, different energy momentum tensors that describe the different parts of your system. And these are beautifully written tensor covariant equations, but the beauty disappears pretty fast when you try and solve them numerically, because even just the first line in that list will provide you a system of equations which in a first order formulation, which is the one we're trying to use now, has 58 variables. So essentially you have partial derivative with respect of time of 58 fields. These can be components of a tensor, or scalar quantities, or vectors, and so on. So the thing is extremely complicated, and that's why you need decades to build the numerical infrastructure that allows you to solve these equations. But luckily enough, I was surrounded by very talented students, and so with some of these students we built a code, for instance, like this one, which allows you to see what happens when two neutron stars get close to each other. You can see that they in spiral, they get closer, and as they get closer, their shape changes. They are becoming more like eggs, or rather olives. These are tidally deformed objects, and then they merge. I'm showing the rest mass density here. They merge, they produce this object, which is the upper massive neutron star. It's like a peanut shaped. It's losing a lot of angular momentum, and because of this is spinning up. And at one point, it is going to become so compact that an event horizon, particularly an apparent horizon, appears. And the matter that you see around it, well, that's what we call a torus. You may think that this is actually a very tenuous gas, but it is not. You're looking at density of the order 10 to the 9, 10 to the 8 gram per cubic centimeters. So in this picture that I've shown you, there are three important elements that are the fact that there is a merger when the two stars touch. There is an hypermassive neutron star that is produced, and then eventually this object will collapse and produce a black hole plus torus. Okay, this picture is a very robust picture. We can put a lot of microphysics and details, but these basic elements of the picture will remain. So you may ask, okay, what are the degrees of freedom in this picture? Well, first of all, the total mass. If you start with a system that has a lot of mass, as soon as the two stars merge, they will want to produce a black hole. By contrast, if the total mass is very small, then you may produce an object which will survive for a very long time, possibly never collapse if they are really, really light.
We have a quick question, a quick clarifying
Sure.
question. Is what do the colors represent in the previous picture?
Density, rest mass density.
Thank you.
Yep. The second aspect is mass asymmetries, okay? And let's see, if you want to understand what is the role played in mass asymmetries, I can show you another simulation here where I am changing the symmetry in the mass by 20%. So there is one of these two guys who has 20% more mass. And if you know a little bit about equations of state in this regime, you realize that it's the small guy, actually the more massive. So keep an eye on the small star. What this will do is that before the merger, it will actually break apart the companion. It will accrete most of its mass. It will spin up and break itself apart, launching a big spiral of matter at large distances. And this is an example of a possible configuration. What you learn in general by having non-equal mass or mass symmetries is that you produce tori which are generally more massive, they are more extended, they are at large distances, they are quasi-Keplerian. And this is simple to understand. You simply have one star that is broken and it's smeared out at large distances, and this allows you to produce this configuration. And of course, that's what you want, because having a matter in a torus is like having a reservoir of energy that you can tap later on to produce a gamma ray burst. Well, equations of state, of course, play an important role in this picture. magnetic fields, that I will explain, play an important role, and radiative losses also play an important role. By radiative losses here, I don't mean photon. I'm talking about neutrinos here, because the temperatures and density are such that most photons are trapped by, but neutrinos may well leave the system and actually bring away mass, energy, well, not mass, but energy and angular momentum. So let me tell you how you can possibly do gravitational wave spectroscopy and understand what these equations, what are the equations of state of neutron stars. So first of all, in order to explain this, I need to give you a very short introduction to the gravitational wave signal of a neutron star binary. This is an example of a waveform, and there is a part which is called the chirping signal, which is the final part of the inspiral, and it's called a chirp because the amplitude grows and so does the frequency of the signal. Then there is the merger, and there is a short transient. The system is still adjusting itself. And then there is the hypermassive neutron star, or HMNS, post-merger phase. And if you recognize this, there's going to be one point where the star collapses and produces a black hole. This is shown here in the ring down. So these are the main parts of a signal. And of course, the size of these parts will depend on the properties of the equation of state, on the mass. I've inserted here, by contrast, a binary black hole signal. And you can see that a binary black hole is much simpler. You have the inspiral, and immediately after you produce a new black hole. So what really distinguishes a black hole binary from a neutron star binary is this all of this post-merger signal. There is a different way in which you can look at this signal, and is in Fourier space. So imagine this is just a function of time, and you Fourier transform it. It would look something like so. I'm showing you frequency here in hertz, and I'm showing you the spectral power density. So this is the amount of energy per frequency bin. And this is the way gravitational wave physicists like to think of signals. So they put some sensitivity curve of a given signal, of a given instrument, and then anything which is above this curve, say advanced LIGO, is detectable. Anything below is not. Okay, let me move this away. What you can see is, suppose that we consider a system of two black holes of 1.4 solar masses. Well, you may say these objects don't exist, and that's probably right. But I need them just to make a comparison with the same mass system of neutron star. And I'm plotting this in black. So at large distances, or if you want a low frequencies, the binary system is just progressing like a power law here. Then it's producing less and less power at a given frequency because it's spending less and less time at a given frequency. The inspiral is accelerated. And there is a non-linear part where the emission is much larger, and then there is a ring down. That's when the merger happens. And you can see that for a binary black hole system of 1.4 solar masses, you have that the merger happens at about 5 kilohertz. Okay, and you are well below the sensitivity curve, so you would never be able to see this. Now, let's imagine to do the same track for a binary neutron star system. Again, at large distances, black holes and neutron stars, they just smell the same. They are point particles, they are moving on quasi-Keplerian orbits. But then as you go down in energy, spectral energy, and go up in frequency, because neutron stars are extended, they will start having different trajectory, which means that the power as a function of frequency will change. And this region over here is when the two stars start feeling each other's tidal field, and at one point they will touch, they will merge, and then they produce this very messy signal over here. So part of the game is being able to tell the black from the blue, and you do this by recognizing tidal effects, which change the gravitational waveform. But more importantly is telling the two blue curves. Here there are two blue curves, which represent two different equations of state. And you can see that, well, you may think that these are very similar and there is little to see or distinguish, but actually there is a difference, and I will explain it. So this is an example of what we can do now with our code. This is a very colorful plot where I'm showing with on every row with a given color an equation of state, and in different columns I'm showing you different masses. So this is APR4 is one equation of state. This is the mass of a single star, 1.275, and it increases in this direction. And you can think that these are soft equations of state. We say that an equation of state is soft if you can compress matter so that for a given mass you have a rather small star, or stiff, which is pretty much the opposite. And what you can see is that soft equations of state will give you a post-merger signal that is smaller than a stiff equation of state. You can see here the signal is much smaller than during the inspiral, while here the signal is comparable, maybe a factor 2 smaller. You can also see that the frequency of the post-merger signal is higher for soft equation of state than it is for a stiff equation of state. And it's easy to understand. A soft equation of state will give you an object which is very, very dense, will oscillate very rapidly, but also rotate very rapidly. And so you produce a very high frequency signal. And you can think that there is a continuum between these two extremes as you consider the equations of state that are, between these two extremes. Now, all I've described you is, I think I've took less than a minute, and yet these simulations took about a year to produce, just to give you an idea of how expensive these simulations are. Another thing that you can see is that if you consider similar masses, this guy or this guy over here, this guy is producing very little gravitational waves, and so this object will be stable for much longer time than this one. In fact, this one will collapse. I don't know if you can appreciate, but at the end here, it has collapsed. So after 25 milliseconds, it has collapsed, while this will possibly resist for something like 200 milliseconds. Now, if you look at those signals in frequency, that's what you get. You see all of these power spectral density, and I don't think you should concentrate on any detail here. But what is important is that you appreciate that there are lines. Okay, so you can think that this is a spectrum which has lines, just like you know about emission and absorption lines in stellar atmosphere. You can think that there are lines in the gravitational wave signals or spectrum, and so you can do gravitational wave spectroscopy. That is, you can tell what are the properties of the object by just looking at the way it rings after the merger. If you're not convinced, let me give you an example that this is possible. So this is an equation of state. Let's call it the blue equation of state. This is the time series. This is the Fourier transform of it. This is the part of the signal before the merger, and the solid line is after the merger. So you have to imagine that the dotted line goes up in this direction. Okay, you can see that the power spectral density has 3 peaks that we, with a lot of fantasy, called F1, F2, and F3. And there is one which is definitely larger than all the others, and you convince yourself that this has to be this part of the signal when the frequency evolution is very small, and so you have a very clear and narrow peak. And in fact, these 2 side bands, they are producing this portion of the signal when the star is adjusting itself. Okay, so this is a spectrum. Now let's consider a different equation of state. Let's call it the red equation of state. I am aligning the 2 equations of state at t = 0 at the merger, and you can see that the inspiral is different and the post-merger is very different. If you look at the spectrum, it's very different. However, you can recognize that there is still an F2 frequency, there is still an F1 frequency, and there is still an F3 frequency. So this is telling us that, if we just knew how to relate the position of, say, the largest peak, which is probably the one you will see first, with the properties of the star, then we have a way of doing gravitational wave spectroscopy. And luckily for us, we can do this. There are what are called universal relations, or quasi-universal relations, that can be found about the values of these peaks and the properties of the star. And these properties, like tidal deformability, quadrupole moment, are independent or weakly dependent on the equational state. So what can you do? Well, essentially you can do a spectroscopic approach to study the post-merger signal. You can do a you can use this quasi-universal behavior. You can use an analytic modeling of the post-merger, and you can ask yourself questions of the type: how well can I constrain the radius of the star, which is related to the equational state, if I have n detections of the post-merger? Now, here you see already how a theorist is an incurable optimist. We haven't seen any of these post-merger signal, but I'm already telling you what you will see when you will see 10 or 20 or 100. And this is shown in this figure, which is a bit messy, but let me just say that here is the average radius. So you can think this is a measure of the equational state. So this is a stiff equational state, large radii, a soft equational state, small radii. And this is the uncertainty in the measurement of the radius in percent as a function of the number of detections. So light color is 20, and then dark and dark is 50 or 100. And on top and bottom, there are just two different instances of a distribution of population. What you can learn is essentially summarized over here. You can already with 10 equations, with 10 detections, you can distinguish between stiff or soft equations of state. If it happens that the equation of state is stiff, then with about 20 detections only, you will be able to measure the radius with a precision than less than 10%. If the equation is soft, then it's much harder to model the signal, and then you will need a bit more, about 50. But if we are so lucky to get a golden binary, say something that we can observe with very high signal to noise ratio, then a single binary, because we will see a very strong signal, will allow us to measure the radius with about 2% precision and 90% confidence level. Of course, statistically this is not going to happen, but it would be nice if that happened.
So we have a quick clarifying question before
Yes.
you go on about these curves. So the question is, how does the unknown neutron star rotation, which is likely to be quite different in the two stars, affect the curves?
Right. So stars, when they merge, they are pretty old. Okay, they've been they are no longer in contact with anything which could give them angular momentum. So we think that in practice they don't spin very rapidly. In addition, if you think about what is the angular momentum of the merged object, you find out that that should be the sum of the angular momentum of the orbital angular momentum at the time of the merger, plus whatever spin they had in the past. And the orbital angular momentum is dominant. It's about 100 times larger than any spin angular momentum for realistic values of the spin. So in essence, spin doesn't play such an important role. But nevertheless, we have investigated what happens if you have extremely large spins. And then what you learn is that this discussion I was making about the position of these peaks changes. There is a dependence on the position of these frequency peaks on the spin, and this is of the order of 5%. So the position will change to slightly larger frequencies if you have, an unreasonably or unexpectedly large value of the spin. Okay, I hope I have addressed that question. Let me go on to talk about electromagnetic counterparts, okay? So what are the electromagnetic counterparts? Well, now we know that every time there is a gamma ray burst, or a short gamma ray burst, I should say, we know that there is a neutron star merging somewhere. This was really, this was a long-standing conjecture that GW 170817 has clarified. Now, short gamma ray bursts or even long gamma ray bursts show jets. Okay, so jets in astronomy tell you that, okay, there must be some magnetic field, large-scale magnetic field. So the point is, what happens when two stars with a magnetic field collide? And, well, there's just one way of finding out, and it is solve the equations of relativistic magneto-hydrodynamics in addition to Einstein's equations. And this is something we've done already a few years back. And this is one simulation that allows you to appreciate what happens. So here I'm showing you two quantities. One is the density with this color code. And here I'm showing you the strength of the magnetic field with this other color code. These are both two scalar quantities. If I were to show you both of them on top of each other, you wouldn't be able to see much. So what I've done is I have made a transparent wall here, and you have to imagine that on either side of this wall, I am showing one of the quantities. So it's always the same binaries, just they change color as they go across this wall because they're showing different quantities. Now, when they merge, you can see that there is a lot of material which is ejected. This is material at very low density but large magnetization. And at this point, you see that the black hole is being produced. I don't know if you can appreciate, there is a little sphere there, which is an apparent horizon. This shows some snapshot of this process. You see the stars have an ordered poloidal magnetic field. They merge. They still have a globally coherent magnetic field. Then there is the merger, and there is this differential rotating object that messes all the magnetic field up. So there is no memory of the dipolar magnetic field as a result of this turbulent motion. But if you continue this simulation further, you see that something happens. In particular, what you can see is that because there is a black hole, matter can here has very little angular momentum, so essentially falls, and by falling will carry with itself some of its magnetic field. Furthermore, magnetic field is growing because there's motion here in the disk, and so you have this combined effect of having material falling onto the black hole and producing an ordered magnetic field and magnetic field strength increasing. And as a result, this is what you see in these snapshots. You see that as a black hole is formed, the magnetic field is still pretty much chaotic. But then as time goes on, you start producing an ordered magnetic field in the disk. And if you wait long enough, you produce an object which has a structure that looks like a jet. This is not yet an outflow. It's just a structure. It's just telling you about the topology of the magnetic field. So these are, simulations that we've done almost 10 years ago. If you look at the properties of the black hole, you have a rotating black hole of 0.8. You have about 6% of a solar mass in the torus. If you calculate what is the accretion time scale, is about a fraction of a second, 0.3 seconds. So all of these numbers are matching the expectation for short gamma ray bursts. So these simulations are in no way trying to simulate a short gamma ray burst, but they are telling you that the basic features of short gamma ray bursts can be captured by having two stars with a magnetic field collide and produce a black hole. Since those calculations have been done, other groups have repeated those calculations, finding again with different degrees the presence of this jet structure. We are not able yet to produce an outflow which is relativistically, matching what we expect. So gamma Lorentz factors of order 100 or so. All of our Lorentz factors are of order of a few at most. Now, how much do I still have? I think I have maybe
you have 10 or 15 minutes.
Yeah. Okay, so I would like to spend a few words on GW170817 because this is a remarkable detection that has taught us a lot, and in particular has taught us about the maximum mass of neutron stars. Now, this is what we've seen, very nice signal here in Livingston, kind of nice signal in Hanford, no signal in Virgo. But nevertheless, this was very important because it allowed us to locate and see the light from this system. So because the post-merger is at high frequency, we haven't seen it. You know, the signal is lost. After this time, there is no more signal. But this information alone, plus the light that we saw 1.7 seconds later, is enough to tell you a very important property of neutron star, that is the maximum mass. I know that, you know, not all of you are familiar with this concept. So let me try to explain this, and I hope to be not too pedantic for those who know about this concept. So here is what we know. We have that the system has 2.74 solar masses. That's the whole mass of the system. How do we learn what is the maximum mass from this? Well, first of all, what is the maximum mass? If you solve the equations, the Einstein's equations for self-gravitating, non-rotating configurations, say non-rotating stars, then you can plot the results in a diagram which has m, the mass of the system, and the central density. And you will have a nice curve like so, with a local maximum. And this is important because this is showing the maximum non-rotating mass. To the right of this maximum, you have unstable configuration, right? To the left, you have stable configurations. Now, if you look at this plot, this is a bit of a funny plot. It doesn't have numbers. And that's because this is a generic feature. Every equational state will bring you this up or down, to the left or to the right, depending on the equational state. But they all will have this local maximum. In this space, m rho, you can produce more solutions to the Einstein's equations. And this is in this green shaded region. These are for uniformly rotating stars. So every point in this green region is a solution to the equations and represents a rotating star, a uniformly rotating star, a rigid body rotating star. And what you can find is that this region is upper limited by another line, which is called the Keplerian limit. So all the stars on this black line are spinning so rapidly that if you spin them just a little bit more, you will break them apart. They will start losing matter at the equator. Also, this curve has a maximum, and this is the maximum mass of rotating configurations. And of course, to the right of this line, you have unstable solution, and to the left, you have stable solution. And you can show that there is a line joining M max and M TOV, which is called a stability line. Anything that crosses this line is doomed to collapse to a black hole. Okay, so this is, why is this important? Well, we don't know what is M max and we don't know what is M TOV, but we know something which is universal. And this is the relation between these two. In particular, we know this universal relation that says that this object, this mass, is 20% larger than this mass. So whatever this mass is this one will be 20%. This means that if we know this mass, we know this mass as well. Okay, a bit more. There is yet another space of solution, which is that of differential rotating stars. And it is shown with this salmon region over here. Now, again, you can show that there is a stability line. And if you cross this stability line, you will produce a black hole. Let's go to GW170817. When the two stars merged in GW170817, they must have produced an object here. Why here? Well, it was very massive. It was certainly larger than the mass of the two stars. And we also know that it produced a gamma ray burst. And you know, in the most commonly accepted picture, this means that you have produced a black hole. And if you follow my logic, this means that your initial model that started here at the merger must have crossed this line somewhere. Essentially, you have two options, you know, the track one or the track two or the track one. In the track two, you cross this line very rapidly in a matter of a few tens of milliseconds. If you think about the first movie I showed you, that's exactly what happened. The hypermassive neutron star was produced. Exactly 20 milliseconds later, you produce a black hole. If you follow this track, Well, it will take much longer. In particular, if you enter this region, the green region, you may stay there for quite a long time, because there you are almost axis symmetric and you are not losing much in terms of gravitational waves. So which of the two tracks is the right one? Well, we think is number one. And the reason is that we've seen a kilonova, and the kilonova was very bright, which means that a lot of matter was lost. And in order to lose so much mass, given that we know how much mass you can lose, you need to have survived at least of the order of 1 second. And there is no way that you can do this if you follow this line over here too. Okay, so let's recap. You consider the evolution track number 2, you use the measured gravitational mass, you remove the rest mass that you know from the kilonova, because that's been lost in the kilonova, and you use universal relations that I was mentioning before to deduce the following upper limit on the maximum mass. So we now know that MT of E has to be between 2 solar masses. This doesn't come from my logic. This is just a measurement coming from pulsar timing. And there is an upper limit of about 2.16 plus or minus an uncertainty. And if you take the strict upper limit, this is 2.33. Okay, so I've given you an argument which is based on a series of logical considerations. Maybe I haven't convinced you, but that doesn't matter, because this very same number has been obtained also by other 3 groups using different logics, either simulations or considerations on the kilonova signal. So although you may not like my argument, you probably should take this number seriously. 2.3 is really what looks like a reasonable upper limit. Okay, I will now come to my last part of my talk, which is about phase transitions. I work in Frankfurt. In Frankfurt, there is a long tradition of people studying, heavy ion collisions, and my colleagues like to think of the universe in terms of phase diagrams. So, they have a diagram where you have temperature and biochemical potential, and you put the whole universe there. So you have early universe over here, you have neutron stars over here, low temperature, high density, you have low energy heavy ion collisions, QCD, lattice QCD calculations. Well, neutron star mergers, you can see, covers an interesting region of this phase diagram. And so you can use neutron stars to probe this region, in particular to probe the properties of whether or not there is a phase transition. And that's what we've done. We have considered an equation of state which allows for the production of quarks under certain conditions. Actually, we can simply switch on. You can see that from this equation, from this mass radius diagram, that I can have a purely hadronic equation of state, which is this one black one, or I can have a quark phase transition and even a mixed phase over here. So what we've done is we have repeated the kind of simulation that I've shown you before, this equation of state, and this is what happens. At this time, in this point in time, the 2 stars are still fully hadronic. When they merge, it's still full hadronic because the temperature and density are not large enough. But then if you look at I'm showing you now the quark fraction, because it is a mixed phase, you see that there is a bit of quarks which are mixed together with hadrons. And now I'm showing you also the temperature. So you have 3 different quantities that you can look at the same time. This is relevant because quarks appear there where the density and the temperature is high. As soon as a lot of quarks are nucleated, then the equation of state softens, sorry, and you produce very rapidly a black hole. This may be a bit easier to read from these snapshots. So, well, maybe. These are also complicated snapshots because I'm showing a lot of quantities. I'm showing you density with these isocontours. I'm showing you quark fraction with this color code, and I'm showing temperature with that color code. And I'm cutting the quantities here so that on the right I show quark fraction, on the left I show you temperature, and these are 3 different snapshots. Okay, what you can learn is that where the temperature is high and the density is high, there are quarks. You can see it here, you can see it here. And at about 15 milliseconds after the merger, you produce a lot of quarks in the core. And when this happens, the equation state softens and you bang, produce a black hole. You can see this very, very clearly in the gravitational waveform. So black is standard hadronic equation state. Red is an equation state where you allow for the appearance of quarks. During the inspiral, there are no quarks because the density are not large enough, the temperatures are very low. And so the phase difference between the two signals is zero. This is shown here. Delta phi is the phase difference between the two gravitational wave signal, and these are the gravitational wave frequencies. But then after the merger, you start producing quarks. At the beginning, they're just very few, but still enough to produce a deformation, a change in the quadrupole moment. And so the gravitational waveform will be different, and you're going to start seeing a difference in the phase. And as soon as you have a full phase transition, then you produce a softening and you collapse to a black hole. So how do you know that a phase transition took place? Well, here is the way you do it. You see the inspiral, and the inspiral makes you think that it's a fully hadronic equational state, which means that you would expect a black hole production at this time. But actually, you see that this happens earlier. So a discrepancy, an inconsistency between what you would expect in terms of inspiral and post-merger signal is going to be a signature of a phase transition. There is very little else that can do this. We've been doing a bit more analysis of this possibility, and actually we have come up with a classification of all the possible scenarios that you can think to reveal an equational state. So the first one is no phase transition. Okay, you have the frequency of the signal goes up as a function of time. It reaches a maximum and then remains high. This is the hypermassive neutron star, which is fully hadronic. Another possibility is that already at the merger, you immediately produce a phase transition, and you produce an object which is stable, but has a much larger frequency than you would expect. This is called a prompt phase transition. You can have a phase transition triggered collapse, which is the one I was mentioning. You have the merger, you have the continuous transition to a new quark phase, and then you have a trigger collapse. Or you can have this other, and is possibly the most interesting scenario, which is called a delayed phase transition. You can see that you produce a merger, you have a fully hadronic system, but then slowly you produce a phase transition, and this doesn't lead to a black hole, but to a new state which is stable and will be oscillating at a higher frequency. To show this is not just a cartoon, these are the results of actual simulations, where you can see, this is a realistic no phase transition case. This is also another case with a slightly smaller mass. Here, this is the phase transition triggered collapse. You see, you have phase transition, and then you have the appearance of a black hole. And this is the other case that I was mentioning, the delayed phase transition. You have a first part of the signal where you oscillate at a given frequency. This is this part over here. And then you transit to another higher frequency value. And although this is not so clear from here, if you do a power spectral density, the evidence is very strong. So, this is a fully hadronic equation state. You have just one F2 peak. And this is if you have a phase transition. You have two peaks, two F2 peaks. The first one is due to the hadronic part of the life of the hypermassive neutron star. And the second one instead is the one of the newly produced quark star. So, having two peaks is a very convincing signature that you actually have undergone phase transition. Okay, I think I should come to my conclusions. Well, first of all, I try to explain that if you look at the post-merger signal, you have a complicated but beautiful piece of information that you can read off in terms of peaks, in terms of lines, and that the behavior of these lines is quasi-universal, so independent of the equational state. If you use these relations, then you can, and of course you observe the post-merge, and then you can measure the radius of the star with a precision of 1 kilometer or less. I've explained that if you have binaries with a magnetic field, then you will lead rather naturally to the production of jets, structures after a black hole is formed and not before. And GW170817 has already given us a number of constraints. This is the one I've mentioned in detail, the maximum mass, but there are also others in terms of radii, in terms of tidal deformability, in terms of the mass necessary to produce a prompt collapse, that is a collapse immediately to a black hole. And finally, I've explained that a phase transition can happen after a binary neutron star merger, and this leaves rather clear signature. And of course, we don't know if this is going to happen in nature. But if it does, then gravitational waves will give us a fantastic tool to probe the phase diagram and to explore quark phase in the universe. Okay, I think I will stop here and take your questions. Thank you for your attention.
Thank you very much for this beautiful talk. It looks like we're ending the academic year with an actual bang. So if you enjoyed the talk, please write something in the Zoom chat or on the YouTube chat. If you're watching on YouTube, I'll be able to share the Zoom chat transcript with Professor Rezzolla at the end. So please go ahead and write some good words for the talk. We already have a question lined up. The first question will come from Professor Jim Klein. Just a reminder to everyone in the Zoom session, if you'd like to ask a question in Zoom, please use the raise hand feature. And if you'd like to ask a question in YouTube, please type it into the YouTube chat. The question will be relayed to me by my sidekick. So please, Jim, go ahead. Oh, I have to allow you to unmute. I tend to forget. So I've changed the security setting now. Jim, please go ahead.
Thanks for that very nice talk. I wondered about the possibility of dark matter accumulating in neutron stars, and if that could affect the kind of signatures that you would see from gravity waves.
Oh yeah. Okay. So it will, and the devil is in the detail. So I can guide you through what I can imagine being at least two extreme scenarios. One scenario where you have the dark matter condensation will be very tightly coupled with the ordinary matter, in which case you can think there's going to be a dark matter core which will co-move together with the ordinary matter, and then the difference will be extremely small, essentially almost indistinguishable, okay? Because these are two tightly coupled fluids working with each other. You can think that the opposite, that the coupling is very weak, in which case you can think that the dark matter core will actually lag behind the ordinary matter as the two stars inspiral faster and faster. And in particular, after the merger, when things really go fast. In that case, you can think that it's going to be, a given distribution of matter and a given distribution of dark matter that will try to follow whatever is the gravitational potential determined by the ordinary matter. And people have estimated roughly what happens. There is a toy model that actually we built to study these frequencies, and that has been employed to study what happens if you have a dark matter core. John Ellis has done this work, and you can see that it is tantalizing to think about what you could see if there is a dark matter. But of course, as I said, the detail is the devil is in the detail, and essentially you can come up with any prescription between the two extremes that I mentioned by just changing the potential of dark matter or the coupling between gravity and whatever is this dark matter field.
Thank you.
Yeah, the next person is Professor Vicky Caspi, and I think she's chomping at the bit. Please go ahead, Vicky.
I wasn't aware I was chomping, but I'm definitely enthusiastic. Thank you for the really, really interesting and clear talk. One question I have is, you mentioned phenomenology of short gamma ray bursts, but there's also fast radio bursts where there's these short radio transients that we don't really know their origin, but I'm wondering if there's any evidence from your simulations you might end up with some sort of radio transient at the time of the merger.
So there is no evidence from our simulations. And I'm in the school of thought that doesn't believe fast radio bursts are associated with binary mergers. And I will explain you why. Actually, I more as a an amusement, together with Aino Falke, I proposed a model for fast radio bursts, which is called the Blitzer model, where we show that rather naturally, if you have a neutron star which has a magnetic field and you collapse this star for whatever reason, then because a black hole cannot have a magnetic field, the magnetosphere of the neutron star will have to be ejected. It is like the magnetic field lines will have to be snapped, and so the magnetosphere would be ejected, move very rapidly as essentially, a discontinuous magnetic field, and while doing so, will produce coherent emission that will peak in the radio, and so not only the time scale of the order of a fraction of a millisecond, but also the frequency will be the right one. So people have used this model to say, sorry, I shouldn't go there, to say that, okay, binary neutron stars will produce an object that will collapse, and so you can produce a fast radio burst in coincidence with a binary merger. I am not convinced. The reason is that in order for us to produce such a coherent emission, we really need a baryon-free environment, which is the one we were envisioning in our model, because we're thinking about an old star, far after the supernova explosion. But as I've shown you, binary neutron star mergers are very dirty and messy environment. You produce a lot of matter around. So even if you, for whatever reason, are able to produce a radio signal, this will be most likely absorbed by all the matter, very high density matter that would be between the collapsing object and this that observed.
Just a quick follow-up. I could be mistaken, but I thought I saw a preprint on the archive by, I think it was Lehner et al., where they also did magnetohydrodynamic simulations of magnetized neutron stars merging, and they do predict a radio transient. So I was so excited, and now I'm hearing from you that you disagree. So I'm wondering, what is the difference between your simulations and theirs?
I don't know exactly which simulations you are referring to. I think I'm not sure whether you're referring to maybe to the pre-merger before Louis Lehner and has indeed studied what happens to the two neutron stars magnetospheres before the merger, and then has shown that the two neutron stars, you can think they are about 100 kilometers in size. They will start interacting before the merger, simply because the stars will reach a separation of a few hundred kilometers. And at that point, depending on the polarity of the two magnetospheres, you can produce a radio signal. But this is really before the merger, when the system is still very clean, baryon-free, and you can produce this signal. But I don't think this is what you would associate to a fast radio burst, because this would be an almost continuous signal with growing amplitude in the radio.
Okay, thank you.
Yep.
Okay, we have one question from YouTube, and then we'll have a question from Gonzalo Alonso Alvarez. So hold on. I don't know if we'll get to another question after that, but we'll get to these two at least. So the question from YouTube is, what would be the effect of mass asymmetry on the fraction of the quark matter produced? And how would the phase transition affect the neutrino luminosity?
Okay, so those are two difficult questions. To answer the first, mass asymmetry essentially will change the situation in two ways. Mass asymmetry means that the system is no longer having a symmetry in mass, and so but when the two star when the hypermassive neutron star will undergo a phase transition, it's going to be a rather different mass distribution, and this will lead to a gravitational wave signal that doesn't have the m equal 2, L equal 2 mode being the dominant one. Most likely the dominant mode in that case will be an m equal 1, simply because you have to imagine that the mass asymmetry will create a one-sided bulge of matter distribution, and this produces this M equal 1. And this M equal 1 distribution of matter will be further amplified when there is a phase transition. So, yeah, I don't, I can possibly, no, for some reason, let's see if I can show an example. Yes, so a phase transition, this is a delayed phase transition, DPT. And here I'm showing you on the top panel, I'm showing you H21, so the 2-1 mode, normalized to the maximum value of the 2-2 mode. And you can see that this is a very small number and around 0. And I'm doing the same when you have a phase transition. And you can see that when the phase transition takes place, that any deformation in the mass distribution will be amplified. And this is, you can see that when there is a full phase transition, there is a larger symmetry, and there is an increase in the 2-1 component. And what I'm showing you is for an equal mass. So you can imagine that when you have an unequal mass, this effect will become much, much larger, maybe a factor 5 or 10. And that would be another signature of the fact that the phase transition has taken place. The second question was about neutrinos. Well, I don't think I am in the position of being able to answer this. You know, neutrinos will certainly be present and produced. How they will affect or how they will differ or whether they will produce a signature, that's hard to imagine at the moment.
Okay, thanks. I think we have one last question. I'm sorry, we don't have time for more. The last question is going to come from Gonzalo Alonso Alvarez.
Yeah. So thanks for the talk. And my question is a bit related to the neutrino. So you mentioned that in this very hot medium that forms, only essentially very weakly coupled particles like the neutrinos may escape. And I was thinking, like, how much does this could this impact observations, in the sense that, let's say we imagine that there's another weakly coupled particle that can also carry energy away. Could we hope to infer its presence?
Okay, so I don't know if there is another particle, what would happen. But let me tell you that neutrinos have two roles. One is, that they carry out energy and momentum. The second one is they, through the weak interaction, they change the composition of the matter. And so they have an impact on both the strength and the properties of the kilonova emission and on the nucleosynthesis that comes later on. I haven't discussed this because I didn't have the time, but the matter that is expelled, that is ejected, well, this is neutron rich and will interact with neutrinos and change its composition and cool and have a number of nuclear reactions. And so at the end of the day, the interaction of neutrinos with this matter will determine what are the properties of the distribution, the abundances of the material produced. That's what we understand and know for neutrinos. If you have other particles, well, in principle, you could tell the presence of a particle if you know exactly what neutrinos do. Unfortunately, we're still far away from having a very precise picture. We are mostly doing right now, a bolometric energy budget type of evaluation of what is the role played by neutrinos.
Okay, thanks. That's interesting.
Okay, thank you very much. For anyone who is not a tenured or tenure track faculty member, please stick around for the après colloque. You'll be able to talk to Professor Rezzolla a little bit more. And before I sign off, please, everyone, just if you haven't already, write something positive in the Zoom chat or on the YouTube chat if you enjoyed the talk. So thanks, everyone who've joined us today in this academic year. We hope to see you again virtually or in person when we restart the colloquia for the next academic year.